Assalamu alaikum, everyone. Once again, welcome to the session. So today what we would like to do, basically, we will start a new topic, which will be actually a part of our total modeling for the single mission infinite bus system dynamic model.
Sir, your voice is coming low.
Still low? Still?
Sir, can you try again, sir?
Why it's coming low? Just a minute. So we would be starting a little different topic today. So actually in the last few weeks, we have gone through this model, that is the single mission infinite bus system model, with the generator being represented by a third order ODE.
Sorry, sir. Sorry to interrupt. Sir, it's being low again. Means sir, it's
Okay,
started
okay.
sometimes, but
Okay, no problem. Is it okay now?
yes.
Okay. So this was omega naught multiplied by omega minus 1, where omega naught was the base angular speed. Of course, I am going through the nonlinear model. And then omega dot was 1 upon twice h. Then there was mechanical input. Then we also considered later on the damping power, PD. And with that, we also had the electrical output from the generator. Then the third one was EQ prime dash. And that was represented by 1 upon TDO dash whole bracket multiplied by EFD minus EQ dash minus XD dash ID. So this was the overall model. And of course, there were some algebraic variables like ID and PE specifically, besides the state variables and constants. So this was the model. And then we checked the linearized model also. For that, we check the eigenvalues, we check the stability, we check how to obtain the linearized model, all those things. So in that model, actually, we came up with two inputs specifically. So the input vector was comprised of this. The first input was considered to be the mechanical input PM. And the second input was the excitation voltage, scaled version of excitation voltage, that is EFD. So because they are part of inputs, so in today's lecture, we will be focusing on the excitation part. We will be starting the excitation part, discussion on the excitation block. So to be specific, we will be focusing on this thing. So this lecture and probably a few more lectures coming up would be based on the derivation of the dynamic model for the excitation systems. So that means we are actually looking for some dynamics for this input variable U. So once we say that would become a dynamic model, so ultimately we will see that this EFD will also become a state variable later on. Okay. Once we are done with the modeling, so we will see that, well, this EFD goes, or it is also included as one of the state variables, and it is no further, it would no further take part as the U variable. Rather, this EFD would become a state variable. And after that also, when we will continue later on, we will see that even this PM, which is coming from the input mechanical side, this can also be taken care of as, or this can also be modeled in the dynamic fashion. And we will see that with the help of that dynamic model, we can also take care of PM, and that PM will also become part of the state variables. That means with the help of the excitation system and with the help of the turbine governor system, we are actually going to have some control over this PM as well as this EFD. Okay. Right now they are uncontrolled. Okay, they are some constant values in our model, in our dynamic model. So to start with, we go for the excitation system modeling. Okay. So the basic purpose of excitation system, as we all know, for a synchronous machine, the basic purpose for using the excitation system is simply to have a control over the terminal voltage. Okay.
Sir, when our EFD and PM will become state variables, then we will get two more equations like this, like EFD prime and.
Actually, it's difficult to say the number because you see, we started this model and we said, I mean, if we only focus on for the timing the synchronous generator, okay, we took the third order model, right? But we all know that actually we can even go for higher order models than this, okay? So if we go for much simpler model than even the third order model, then we would be satisfied with the second order model, that is the classical model, okay? If we want a little bit more dynamics involved in our model, then we include the third equation. Similarly, if we want a fourth order model, then probably, I mean, for the generator itself, then probably we would go for ED dash dot, okay? So we all know that we had a much more complex model. Then we simplified one after another, and which, I mean, few steps of simplification, we obtained this third order model. We all know that we have 2.1, 2.2, all those models, right? So similarly, this exciter block model or exciter dynamics can go to a very complex one, okay, like third order or fourth order or even higher than that. But ultimately, we will see that, well, for our course, we will be satisfied with a first order model for this. But before obtaining that first order model, we need to know how actually we are going to start the development of the overall model, overall dynamics. Then slowly we might go for simplification. And like we obtained, as we obtained the third order model for the synchronous machine, similarly, we would be satisfied with probably a first order model for the excited dynamics. And similarly, like in the case of turbine model or governor model, we will be satisfied with much simpler dynamics. Okay. So actually the dynamic may vary. Okay. It might be third order on its own, but probably we would be satisfied with the first order model. It could be also fifth order, depending on which blocks from the excitation system, overall excitation system, which dynamics you are actually focused on or interested on. Okay. But at least when we say it is dynamics, at least you should get one single equation, dynamic equation for each of these EFD and PM. Okay. At least you should use at least first order for EFD and first order for PM, if not more. Okay. Shafi?
Yes.
Okay. Okay, then what is the basic purpose of excitation system? So if you want to list the job of excitation system, basically you can list a few. First of all, as we all know that we want to have some excitation power. The very simplest representation of some excitation system would be a simple DC field or DC voltage source in series with some sort of variable resistance. Okay. So this is the very, I mean, if you go for the very simplest one, then you can model it like this. You have a constant voltage source. Because it is synchronous machines, we all know that we can provide some DC voltage in the DC field winding, which is the rotor part of the synchronous machine. So VDC, and of course, you can have some field resistance, variable field resistance. And this, you can also include some coil, of course, there will be some coil, field coil. So let's say this is the field coil. So RF is the field resistance, LF is the field coil inductance, and then this is your final output that is going to excite the coil. So this is the representation of your excitation system. So basically what we need, first of all, we need to show in our excitation system that we have some sort of excitation power. Okay. Secondly, what we need to do, we need to show that we have some control over that. So basically, if I go for the simplistic model, so this RF variation in RF, we can say some sort of, it is giving us some sort of control over the excitation power, right? So we can say that, well, there is some IF flowing out of the circuit, and this IF can be varied simply by varying this RF, keeping this excitation voltage VDC constant over here. So the excitation system should provide us some excitation power, that is VDC provided by VDC here. It should provide some control, and of course, it should provide some protection. So in short, these are the very basic jobs that should be done by the excitation system. By protection, what do we mean? Let's say several kinds of protection are there based on the safe zone of operation for the synchronous generator based on limits. So there are certain limits that are to be satisfied to keep the generator operation within a certain limit. And that limit is obtained simply by the study of the capability curve. That is a synchronous machine capability curve. So that would be obtained with the knowledge of the capability curve. For example, you have megawatt power limit for the turbine, you have MVA limit for the stator, you have like you have field excitation limit, okay, under excitation and over excitation limit, and so volt per hertz limit, and so on. So there are some practical limits associated with your operation of excitation system. So overall, we have three jobs. We have to get some excitation power for the excitation system. We have to get some sort of control, okay, for controlling this power. And of course, some protection job has to be done by the excitation system based on the limits provided by the capability curve. So now we all know that the power or the excitation power that is provided to the field of the synchronous machine is basically DC. Okay. So it is basically DC power or DC excitation. So now the question comes that how are we actually going to get this DC power, and how actually are we going to have some controlling effect on this DC power? Okay, so let's see. So based on the difference in the ways of obtaining the power to the excitation circuitry and to have some control over the excitation power, there is a list of classification for the excitation system. Let's look into that. But the main thing we have to keep in mind that ultimately the power that would be fed to the field of the synchronous machine, that should be DC. Okay, we have to obtain in some way we have to obtain DC power. So there are some basics related to the excitation system that I have just mentioned. This is the necessity of the exciter. You can go through that. These are the functions. As I mentioned, we have some control functions, you have some limiting functions, and the protection functions. Basically, once the limit fails, okay, once the limits are violated or about to be violated, and that is detected by the protective devices associated with your synchronous machine, then the protective functions should be energized, and that specific device or that specific part of your power system should be isolated so that there is no further damage to the system. And I just talked about the capability curve, and from the capability curve, basically you get these four information. So number one, you get the information about the MVA loading, okay, how much MVA loading can be put on the generator. Okay, and that MVA loading is actually translated into the stator heating limit. Okay, that means how much current you are actually getting out of your synchronous machine. And once you are getting the current, so due to that current, you are actually getting some I²R loss in the coils, and that is translated into stator heating. So if you load your generator beyond that MVA loading limit, maximum MVA loading limit, that means you are going to increase the stator heat on a continuous manner. and that would ultimately create chaos for the machine. Second one is the megawatt loading, but that megawatt loading is not actually associated with the generator itself, but the prime mover. Okay, so the prime mover, remember, always it provides the real power, and real power is always, I mean, mechanical power is always the real power. There is no reactive mechanical power. So that megawatt loading limit is associated with the turbine maximum rating, and that's why it is also known as the prime mover limit. And that can easily be obtained with the help of this formula over here, very basic formula. If you know the MVA rating for the machine, if you know the power factor, rated power factor for the machine, then you can simply multiply that rated, the rated power factor for the generator, and whatever MVA rating is there for the generator, if you multiply, you simply get the megawatt loading. Then the third one is the steady state stability limit. And those who have, I mean, I am sure that most of you have taken some undergrad course on power system, and in those, one of those courses, probably you have come up with this knowledge of steady state stability limit. It is nothing but the angle beyond which your your machine doesn't remain in steady state stable zone. So, and that relationship is basically the PE versus delta curve for a synchronous machine. And that is the very simplistic representation. That means where you represent PE as a pure sine curve. So basically we represent PE equals to P max sine of delta. So based on some analysis, it could be found easily that if you operate in this zone, of course, this is 90 degree, this is a sine curve. So this is 90 degree, this is pi, and that is your 0. So the middle point is actually pi by 2. So when delta equals to pi by 2, you reach at the peak of the curve. So that means you are reaching at the P max value. So as long as your machine operates to the left of the peak of the curve here, then you are in the steady state stable zone. However, if your operation reaches here, your operating point is somewhere here, then your system is steady state unstable. Of course, there are some analysis there. So you have to make sure that your system operates to the left of this pi by 2 point, where delta equals to pi by 2. So in the P versus delta curve, you should operate to the left of that middle point, or the maximum P max point. So that has to be ensured. And the last one here, that of course you are exciting the field circuit, that is a coil, and the coil of course can carry a certain amount of current. Okay, so the field current has to be within a certain limit. Otherwise, what would happen? Your rotor circuit would be heated. So the stator heating is based on the armature current or the load current, and the field current or the rotor heating is of course related to the field current or maximum field current limit. So in the nameplate data of the synchronous machine, you would probably get, of course, the rated MVA. The prime mover megawatt rating could also be written, because the prime mover would be, of course, attached to your synchronous machine. So whatever prime mover, let's say in the lab, if you are running a synchronous machine, probably you would use a motor for as a prime mover. So the megawatt loading could also be calculated, or could also be seen from the nameplate data of your motor that is used in your lab for the job of prime mover. The third one, you have to make sure this for steady state stability. And the fourth one is associated with the, of course, this should be given in terms of probably some field current, maximum field current limit. Sometimes it is also provided in terms of voltage, okay, how much maximum voltage that you can put to your field circuit. So all these information are obtained from, could be obtained from the capability curve, synchronous machine capability curve, that is applicable both for the generator as well as the motor, synchronous motor operation. Now, next, let's look at the schematic of the excitation system. So what are the different blocks associated with the excitation system? So first of all, we all know the thing, we start from the thing that we all know about, that is the generator. And by generator here, we mean the synchronous generator. And the synchronous generator is providing some power to the power system. Now, where is the location of the exciter? Of course, the synchronous generator has some armature circuit and some field circuit. So the exciter would, of course, provide the power. If I divide this into two blocks, so we have some field circuit and we have some armature circuit. The armature circuit will ultimately provide you the output power. There is a three-phase output. The field circuit should be getting the excitation from the exciter block. So this is the field circuit excitation coming from the exciter block. Now there should be some control over the excitation power. So the exciter block is actually responsible to provide the excitation power. And the control of this excitation power should be coming from the regulator block. You can also call it voltage regulator. So when we talk about some sort of control, and specifically the closed loop control, we should set some reference point. So the voltage regulator will operate based on some error information, and that error should be calculated based on this reference value. So what it is doing actually, it is taking some terminal information out at this point. So let's say the power P terminal out of the generator that is going to the power system, V terminal that is available at the, let's say, line to line or line to phase, whatever. It could be three phase also. So some information, some sort of information should be extracted about the voltage here, because we are talking about the excitation system. So we are focused about the VT. So that terminal voltage should be fed to some transducer circuit. What is the job of the transducer? Simply what it would do. Remember, this is three phase. So probably the transducer, it will take a sample out of VT, or we can say it will rectify the VT, filter it out, and make some DC equivalent voltage, probably with some stepping down effect. So a sampled value of VT would be taken back or fed back to this voltage regulator for control purpose. So ultimately, a sampled form of VT should be available, which should be compared against this reference value. So whenever there is any deviation between this VREF, let's say this is VREF, and whatever VT is available here. So let's say there is a comparator, and this value, this VT is actually fed to this point. So let's say VREF is plus, and this is the negative feedback VT, of course, after the transducer stage. And then that value is actually fed to the voltage regulator, that is the controller of the excitation system. And as long as there is no deviation between VREF and VT, that means whatever error is generated, E, let's say the error is E. So as long as the E is 0, there is nothing being done from the exciter. But as soon as there is any deviation between VREF and VT, that means there is some non-zero E. So the excitation system should get energized, and accordingly, the field excitation should be updated. This is how actually this block, the transducer block, works, and the voltage regulator does one of its job. So one of its job is to basically take care of this error, okay, take care of this error and initiate some signal to excite or to energize this exciter more or less, depending on the deviation, depending on the error. If the error is plus, means what? Means your VREF, remember VREF is constant. So if the error is positive, that means VT is less than the reference set point. So then what you have to do? Can anyone mention? If VT is less than VREF, then E is positive. So what should you do in the exciter circuit? Should you increase the excitation or should you decrease the excitation?
So increase the excitation.
You should increase the excitation, because in general, the voltage E is function of K and phi. Okay, so we are talking about phi actually. N, we will take care of N from the prime mover side, not now. We are simply focusing on this phi, excitation flux or field flux. So because VT is less than the desired value, so you should increase phi so that VT or this E goes up and tries to catch up with this VREF as soon as possible. So that's basically this block. Okay. So there are some other signals being fed back. So let's talk about those a little bit before we go further. So there is another block inside this transducer that is known as load compensator. Okay. So the load compensator basically is nothing but could be modeled simply, let's say as this, R compensator plus JXC compensator. Okay, so that basically takes care of some voltage drop. So let's say if we want to draw the equivalent circuit of a generator, I'm talking about the job of load compensator now. So the stator circuit, pretty simply, per phase equivalent circuit could be drawn in this manner. Okay. So once this is loaded, let's say the load is here. Of course, this is the per phase equivalent circuit. Let's say the load is here. So as soon as there is loading, there will be some current, right? Let's say this is the internal voltage, E, some internal voltage for the generator. Magnitude and angle, some angle would be there. And this is the terminal voltage V. We just talked about VT, so let's keep it as VT. And this is the machine resistance, the stator resistance, coil resistance, and stator coil reactance. Let's say we are talking about some steady state scenario. This is XS or JXS, whatever, JXS. So this is the stator coil representation. Now there is some armature current IA. So at this point, should there be any difference between E and VT, or they would be exactly same? Of course, E is a phasor, so it has, let's say, angle delta. And let's say VT is angle 0, something like 0. So of course, IA is a phasor. So the question is, will there be any difference between E phasor and VT phasor or not under loaded condition?
Yes, sir, there will be difference.
There will be difference because of this IA, okay? And we can simply apply KVL. And let's say if we simply write in terms of phasors, and if we simply say this is ZS, just to save our time. So ZS multiplied by IA plus VT phasor. Okay, now what is the job of load compensator actually? Let's see. If we are interested only on VT, only on the information of VT, okay, then we don't have to bother about the compensator, okay, because VT is already available to us. Probably we may use some sort of potential transformer, and that potential transformer is enough to provide us the information of VT, because that is available at the terminals, remember, okay, that is easily available or accessible to us. The problem is, let's say if we want to find out the information of some internal variables to the machine, okay, other than this VT, let's say if we want to directly control or directly access some information about this voltage right at this point, which is internal to the system, then how can we extract that? Simply with the extraction of VT, that is not possible. So what we can do, we can simply say, well, if this is ZC, we can simply make ZS equals to ZC, or ZC equals to ZS, because ZS information is available to us. ZC is dependent on us. What is our actually requirement? So if our requirement is to extract the information of some internal variable such as E within the machine, then we can use the potential transformer value, that is VT, and we can set our load compensation block ZC just equal to ZS to directly get the information of E. Of course, IA, that is the armature current, that is also accessible with the help of ammeter over here. Okay. So you see, the load compensator actually allows us to measure or to get the idea of different values or different, let's say, voltages, for example, different voltages at different parts of the overall power system other than the terminal. Exactly. If it is at the terminal, if our interest is only at the terminal voltage, then the load compensator, let's make it 0. If we are interested at some voltage which is closer to the generator, okay, which is closer to the generator, from the terminal closer to the generator, then you put RC and XC positive, because in that case, you are actually looking for some voltage higher than the terminal voltage. So you have to allow some drop to get that voltage. Okay, you have to allow some drop. And in this case, if we are interested in E exactly, then simply if we set ZC equal to ZS, we are done. On the other hand, if we are interested at some point which is away from the generator towards the power system, away from the generator terminal towards the power system, not inside the generator. Now we are looking beyond the generator terminal into the power system somewhere. Let's say the network, there is transformer, there is network, and there is big network, let's say. So let's say if you are interested here, okay, if you're trying to control some voltage here, trying to extract the information of the voltage here, and then if we are trying to put it into the regulator, okay, just for comparison purpose and for regulation. So in that case, what should you do? You set ZC equals to this. Are you getting the point? And in that case, this would be, let's say this is our E, some different E. Let's say this is E1, which is at the secondary side of the transformer. So we are not interested in VT, but now E1 can be simply obtained with the information of VT and of course with the information of I. Remember, this is I coming out of the generator, that is the armature current going to the load. This is the load. And the current is flown, of course, through the transformer, that is step up because it is in the transmission level voltage. So this is a step up transformer. So we are looking at E1 information, and that E1 can be simply calculated as VT minus the compensation voltage multiplied by IA. And in this case, the ZC would be simply the transformer information, the transformer impedance. So ZC would be simply Z transformer. So in this way, load compensator actually helps us to get the compensation value or get the information about the drop due to the load current in different parts of the power system, and extract the corresponding voltage information away from this terminal, either into the generator or away from the generator into the power system. So in both cases, we can play with the RC and XC values, and you can take the corresponding value of V and feed it back to the regulator. Any question? No question. Okay, so let's move on. So that is job of the load compensator, that is usually put within the same block as the transducer. Next is the limiter. If we go up, is the limiter and protective circuits. So as we just mentioned, limiter, there are several different kinds of limiter. One is overexcitation limiter, simply known as OEL. There is UEL, under excitation limiter. There is volt per hertz operation limiter. There are also different other limiters like wind up and anti-wind up limiters and so on. And besides that, we talked about the capability curve. So the capability curve is also there. The limits associated with the capability curves are also there. So there is capability curve, synchronous machine capability curve. So all these, and within that you have some heating limits, okay? Field heating limits, stator heating limits, turbine maximum power limits, steady state stability limit. So all these limiters you can put together. Of course, they form different circuitry. Okay, OEL forms a different circuit for the limiter. UEL is a different circuit for the limiter, and all of these actually have different circuitry for implementing their own limiting operation. But for simplicity, these are not shown here. Okay, these are not shown here. So this is a simple block diagram. And again, the protective circuits. The protective circuits are basically there as a secondary option, because if your limiter fails, or if your operation is somehow your limiting operation fails, then your protection device should be energized, and that should trip a certain part of your, or certain element of your power system, or certain element within the generator block, depending on where the problem is. So that is the job of the limiter and protective circuit. The job of transducer and load compensator is done. Job of the generator and exciter is done. A regulator is done. And the last one that is left is the power system stabilizer. This is a supplementary control signal. This is a supplementary control signal, which actually helps in stabilizing the power system operation. So after actually the excitation design of the excitation dynamics, we would simply jump into the power system stabilizer design, and then we will be going for the turbine dynamics and governor dynamics and all those things. So this block would be taken later on. Okay, power system stabilizer. So what it does basically, it takes some signal as feedback, processes the signal, and then it takes the signal to the regulator block for comparison purpose again. And based on the comparison, if there is some error, it provides regulator excites the exciter further, either in the positive mode or in the negative mode. That means either plus EFD or minus, or plus delta EFD or minus delta EFD. And accordingly, your generator excitation is updated and you can ensure stability based on that. So that is some supplementary control circuit. We would look into that later on. So these are the different feedback signals that is taken care of by the regulator block. And then the regulator actually controls the power fed to the exciter. Ultimately, that controls the excitation field of the generator. So this is how it goes. Then let's look into the types of the exciter, different types of exciter. As we said, our main excitation power should be DC. But with the advent of time, actually there are different types that are being designed by the power system engineers. So to start with, the very old ones are the DC excitation blocks or DC excitation systems, because as we know, we only need DC, and probably that was famous before the advent of the thyristor and the diode, all those things, or all these power electronic or semiconductor devices. So before the advent of all those things, that is the rectification concept of rectification with the help of the power semiconductors. These were the only exciter blocks available in the market. Now then, once we have the AC generators available and the rectification system being developed, so we go for the AC excitation, and all these DC excitation and AC excitation, they could be rotating. There could be some rotating parts in the excitation block itself. The static exciter block is the most recent ones, where within the exciter system, there is no rotating part. Okay, so there's a difference between static exciter and AC exciter. So the most ancient one is the DC exciter, and the most recent ones are the static exciter. And there are, of course, different well-established models proposed by IEEE with different names, okay, for all these. So I will share a paper that is IEEE Task Force Committee report, where you may find further detail on the different models available or models that are proposed by IEEE Task Force Committee. That is some additional reading, of course. So now let's look into the DC exciter. So in the DC exciter itself, here, of course, you get the power, you get the excitation power simply with the help of the DC generator. Okay. And because you are getting the power with the help of DC generator, that power is being fed to the rotor of the synchronous machine. By rotor, we mean the field circuit of the synchronous machine through the use of slip rings. Okay. So in the DC generator mode, you get the presence of slip rings. Now the exciter itself, okay, remember the exciter itself could be driven by a separate motor as a prime mover. Okay, remember the exciter is nothing but a generator. Okay, the exciter itself is nothing but a generator. In this case, they use the DC generator directly. And to get output from this DC generator, which is our exciter, of course, you need some prime mover. So the prime mover could be a separate motor, external motor, external to the setup, or it could also be the shaft of the main generator itself. Okay, that means the exciter could be situated on the same shaft of the main generator or the AC or synchronous generator itself. And this could be either the self-excitation case or separate excitation case. As we all know that the DC machine could be self-excited or separately excited. In case it is self-excited, then the exciter field is supplied by a separate, as we all know that separate excitation means what? Separate excitation means you need to have some external source that would energize the field circuit. And because it is a DC machine, so you can simply draw it. And this is your armature. And of course, the prime mover, as we said, prime mover could be a motor or could be the main generator itself. So the shaft could be coupled to a different motor. Here I have drawn it, or it could be also on the shaft of the same machine or the same generator, the main generator, that is the synchronous machine itself. So now if this excitation, this voltage is actually our excitation voltage here. So that is the EFD. Okay, we're talking about the EFD. That means this would be fed to the field circuit of our synchronous machine. So this block here is actually the exciter block. And this would go to the field of the synchronous machine. Okay. So if it is a separate excitation case, then the exciter field means this field. This is the exciter field because this is the exciter block. The dotted block is the exciter block. So this is the exciter field. So this field is supplied by a pilot exciter. That means this excitation is actually energized from a permanent magnet generator. Okay, from a permanent magnet. So that DC is actually obtained from a permanent magnet, PM type generator, permanent magnet type generator. Okay. Now, in this case, in case of the DC exciter, whatever voltage regulators are used, there could be different types. In earlier days, the model that they used was the rheostatic type, okay, variable rheostat or potentiometer type. And the latter ones used actually different stages of the magnetic amplifiers or the rotating amplifiers. This type was actually, as I mentioned, widely used up to 1960s, but then mostly these are replaced by their counterparts, the AC exciters or the static exciters. But still probably in some cases, we may find that use of DC excitation. So that's why probably we would go through the modeling and we would go through the schematic. So this is the schematic for DC excitation system. And in this case, we have a pretty old device, actually, which is known as the Amplidyne, which is nothing but one sort of rotating amplifier, a rotational amplifier, okay? Based on the motor generator concept, combo of motor generator concept. And it has some special construction. I'm not going into the detail of that because that is not our target. But the main thing that is of that information that we should extract out of this is the Amplidyne is actually providing you some sort of control over here to the field circuit of the DC exciter. So this block is basically your DC exciter, which is nothing but a DC generator, okay, remember. So the DC generator, like the DC generator, any DC generator, you have an armature and you have a field. The field has to be energized. In this case, the energization is done. Is it a self-excitation or separate excitation? This is the question. Anyone? Can you answer? Is this configuration, is it a self-excitation or separate excitation?
Separate excitation.
Separate excitation. Why? Can you explain?
The field circuit and armature circuit is different.
No. Actually, it is a schematic. I mean, the connection is not shown here. Okay. But if you follow, yeah, I mean, your logic is fine in one sense because they are not connected. Okay, that is fine. But it is not actually drawn following that concept. Okay. So it is actually self-excited. Why? Because you see this field excitation, this field voltage or the field current that is coming to this point is actually coming from here. Can you follow?
Yes, sir.
So it is actually the example of self-excitation, okay, not separate excitation. In all the diagram, you will actually not find the connection between them. But sometimes they are separate excited, sometimes they are self-excited. You have to follow actually the power of the field circuit, where it is actually coming from. Okay. So this is the source of the power. Okay. Through this, ultimately it is going to the field exciter. So this is actually being fed back. Whatever voltage is being produced at the armature, DC voltage, that is being fed back through this path. So that is one way of self-excitation, one example of self-excitation. Okay, so this is the main generator then. So whatever DC voltage you produce from this combo, you are feeding it back. You have some sort of control over here. That means if you vary this field rheostat, of course, the current through this path should be controlled. Okay, and these two are nothing but the field of the amplidyne. Okay, so the field coil of the amplidyne, it is being controlled with the help of the voltage regulator. Voltage regulator will provide some non-zero signal. Okay, that means some change in excitation of this amplidyne field based on this information that is extracted from the armature terminal. So you see there is a CT for extracting the information of the terminal current or output current of the generator from the generator, and there is a PT to extract the information of the voltage. So you can say we are actually getting the information being extracted at this point with the help of CT and PT. So take this information, feed it to the voltage regulator. Of course, voltage regulator internal circuitry is a bit complex. It's not so straightforward, but we are not, for the timing, we are not going into that complexity. Just we are showing the schematic. So this VT is now fed back to the voltage regulator, and the voltage regulator power supply actually comes from the output of the exciter. So this is the power supply for this direction provides you the current that is required for energizing the voltage regulator. And this VT, you compare it, you take it, you compare it with the reference, and then if there is some error, you change the excitation of the amplidyne, and accordingly the amplidyne will provide some change in the output voltage. Okay, so this is one way of control here. There are two ways actually. Another way of control is manual. So this is automatic. The voltage regulator operation, wherever you will see control through voltage regulator, we will call it automatic regulation. And wherever you will see some sort of rheostatic sign like this is manual control. So if due to some reason the amplidyne control fails, then this should be operated manually. Okay. So in general, this should be a fixed value from this field rheostat, exciter field rheostat. This should be a fixed value. But once, or if in any case amplidyne fails to provide you the required control, then you may vary this. Okay, and accordingly there will be the variation in the field flux if you change the field resistance of this path that is taken from the terminal of the exciter. And the slip ring is there just to help you out to pass the signal from this part to that part. Okay, any question?
So sir, amplidyne is some kind of what? I mean, is it a device of some sort?
Amplidyne, yeah, amplidyne, metadyne, these are actually some old devices. Okay, these are some very old devices which are nothing but some sort of, which provide you some sort of amplifier job. But it's not like the amplifier that we are used to, like transistor amplifier or the op-amp type amplifier. It is rotational amplifier. Okay. So before the advent of all those things, just I mentioned, transistors or semiconductor devices, the amplification job were to be done either mechanically or electrically. Okay. So the electrical amplification, you can say this is rotational type, and the amplidyne provided you that sort of amplification in the signal, required amplification. Okay. If you want to study further in amplidyne, probably you will not find it in practice. I don't know, probably in Bangladesh and in some other I mean underdeveloped country, probably they are still using this type of amplidyne type of things, or some old power stations, probably the installation is there, so they haven't changed it. Probably you will find this. So we don't need to bother too much about amplidyne, but if you still are interested, then all these topics are actually taken from the Prabha Kundur book. Okay, I will share the book with you, And the excitation chapter, there is a little detail on amplidyne. Like there is DXCs and QXCs. The QXCs are short, DXCs are not short, and further detail could be found probably in some books, but I'm not interested in discussing these things. Okay, it is additional reading for you. If you are interested, you can look at that. Okay, so with the advent of time, this type of devices are now becoming obsolete. So let's go further and go into the AC excitation block. So in the AC excitation, the name of AC exciter means you are going to use some sort of alternator or AC generator as the source of your excitation power. Okay, in the previous case, it was DC. You see the DC exciter. So generator itself was DC used in the excitation block. Now we go into the type of AC excitation. So the first thing is you should use the alternator as your source of excitation power. That is the AC generator. Now again, what is the placement of exciter? Again, you can say usually this is the case that exciter is placed on the same shaft as that of the main generator. So then this could be because now you are providing AC output from your main exciter, but as we told earlier that we need DC to excite our main generator field. So what you have to do, you have to provide some sort of rectification. Again, rectification could be of different kinds. If you use simply diode, then it is uncontrolled. If you use something else than diode like SCRs, then you can, of course, implement some sort of controlling of the firing angle. So based on that, there could be two cases: the output of the exciter, because it is AC, so you need rectification. The rectification could be either controlled with the use of thyristor-based rectifiers, or it could be uncontrolled with the use of diode-based rectifiers. Now, again, the rectifiers itself could be stationary or rotating. So in total, there could be 4 combinations. I mean, stationary controlled, stationary uncontrolled, rotating controlled, and rotating uncontrolled. So based on this combination, there are actually many classifications of AC excitation system, which are proposed by IEEE committee. And also, which I actually missed there, in the DC excitation also, there are some classifications. Okay, there are some classifications. Okay, so then we have the AC excitation block. This is one example of the AC excitation system, one of the examples actually, where you see that, well, this is the main generator again. This is the main generator. So in the main generator, we have one armature and one field. Again, the generator output is actually recorded with the help of CT and PT, and that information is taken to the AC voltage regulator. Why it is AC voltage regulator? Because this PT will actually give you the AC voltage. Again, there are some automatic control and some manual control. The DC voltage control, the DC voltage regulator is purely manually controlled. Okay, you see this potentiometer and this arrow. As I said, wherever you see that, that means it is some sort of manual control. So this is manual control. And there is some mutual exclusivity between these two, normally closed and normally open magnetic contactors. That means when the AC voltage regulator is closed, your DC voltage regulator is opened, this contact is open, and vice versa. Okay. In general, the AC voltage regulator gets the first priority because the output is AC. So the AC signal, AC voltage VT is taken into the AC voltage regulator. The information is extracted. There is transducer and other things. So the path is closed now. So that signal gives or goes up to the control rectifier block. This control rectifier block actually controls the excitation of the AC exciter itself. This is the AC exciter block. Is it self-excited or separately excited? This one?
It's self-excited.
It is self-excited once again. You see this voltage, the output voltage of the AC, that is the AC voltage, of course. AC voltage is taken and it has to be rectified because it is an AC generator. So the field is DC. Okay, the output AC from the armature, but the field is DC. So that's why you need to apply this rectification here. And you can have some controlling effect. That controlling effect would be provided by the AC voltage regulator in general, or in case this AC voltage regulator is not working, then the DC voltage regulator should take care of the operation for further steps. And there is some manual controlling, and then this path would be closed, and ultimately this would provide you the firing control, firing angle control. Why it is needed? Because if you can vary the field current here, if you can vary the exciter field current here, then of course the output voltage here would be controlled, isn't it? You will have some output control here. And that would actually, if you can control this output, you can say, well, this is AC, it is being passed through the stationary diode, that is the stationary rectification block, and then it would be provided to the main generator. So the control of this terminal voltage VT in this case is obtained not in a straightforward manner. Rather, the control is provided in this manner. So you are getting the control in the excitation in the VT terminal voltage of the main generator through the control here. Okay, so you are controlling IF of the exciter. That means you are not actually directly controlling the IF of the main generator. You are controlling the IF of the exciter. That is giving you some controlling effect on this output voltage of the AC exciter, which is AC. Then this AC is rectified. You are getting the DC where there is no further control. So the actual control is happening here with this block. And when the firing angle will change, whenever there is any VT other than the AC reference. Okay. So there is a reference set point. The voltage regulator will compare that reference set point with the actual VT. And once there is any deviation, then it will provide some delta IF or change in the firing angle here. Okay, so the firing angle circuitry will be energized, and then you will have some updated value of IF. Accordingly, you will have updated value of V here. And that would ultimately control your field current for the main generator. Okay, any question? Okay, there are some auxiliary input, of course. The auxiliary inputs are required. They actually come from your limiting circuits. Okay, so they are actually doing some job for getting information about the limits associated with the generator, whether your operation is within the limits or any limit is being violated, and these things. Another example is, it is still the AC excitation system, but here you are getting what? The difference is here. Where are the differences? So now you see the control is here. You have two control parts. One is here on the AC exciter itself, and you also have some control here. So it's a dual control type device or type system. Okay, so the DC voltage, AC voltage regulators are there as before. You have the CT and PT, you have the main generator block, you have the slip ring, and it is still stationary, but could be rotating also, as we mentioned. So this control is now coming. So now you see this AC voltage regulator or DC voltage regulator is actually controlling this block over here, the rectification block, which is a controlled one now. So the firing angle is directly being controlled now with the help of this AC voltage or DC voltage regulator with the information of VT, of course, the terminal voltage and AC reference. So, and of course, the AC exciter itself has its own control. It has its own control. So again, it is taken some information with the help of some PT or some transformer, and that is taken into the exciter regulator. Okay, this is the exciter regulator, like the voltage regulator. Okay, similar like the voltage regulator, we have some additional regulation here because there is some control. Okay, So that creates further controlling effect here. So this is the difference with the previous one. But it is still AC. Means your exciter is an AC machine. It's not a DC machine. And your rectifier block is stationary. Still it's stationary. Now we go to the next example of AC excitation, which is known famously as brushless excitation system. And that is having some rotating structure. It is still the AC excitation system, but a little different than the previous two. Here we have a rotating structure with some pilot excitation block. So here you will have 3 armatures. Previously you had 2 armatures. In the previous two, you had 2 armatures. You can see 2 armatures. One was the AC exciter, another one is the main generator. Previous than this one was this. Still you had 2 armatures only. Again, you had AC exciter and main generator. This is a little different, the brushless excitation system, where you can see that, well, you have a pilot exciter, you have an AC exciter, and you have a main generator. So you have 3 armatures. Okay, so now let's give the blocks, boundary of the blocks. So this is your main generator. It has a field and it has an armature. This is your main synchronous generator. Again, CT and PT are there, and that information is taken into the AC voltage regulator. And because the intermediate block here is rotating, so this rectangular block here is rotating altogether. That means the field, this uncontrolled rectifier block, this armature, as well as these permanent magnet, north and south, this is permanent magnet. So the permanent magnet, all these 4 parts are actually rotating. This is stationary. Anything other than that are stationary. Armature is stationary. This is stationary, but the field is moving. This is stationary, but this is rotating. So because it is rotating, we can't take any signal, and there is no DC voltage regulator also. So you only have the AC voltage regulator in this case. There is no brush, remember. So that's why it is known as brushless excitation system. Okay, now, as we all know that for each of these devices, like as I mentioned, just for the main generator, we have a field and we have an armature. This is the field of the main generator. This is the armature of the main generator. What about the AC exciter? The field of the AC exciter is this one, which is stationary. The armature of the AC exciter is rotating, which is this one. What about the pilot exciter? Pilot exciter field, this field is actually not the field of AC exciter, remember. Although they are shown in the single block, but that is not to mention, that is not to mean that this and this belong to same machine. This armature belongs to AC excitation system, and this field belongs to the AC excitation system. So this is a single block. And this armature and this field, this belong to pilot exciter. Are you clear? So you are having 3 armatures and 3 fields. That's the first thing. 2 of the fields are rotating. Okay. 2 of the fields are rotating. One is this and another one is this. One field is stationary. 2 of the fields are electromagnets, this field and this field. One field is permanent magnet, that is this field, pilot exciter field. Okay, so there's a little difference between them. So this is the boundary for the pilot exciter block. Now, because this is rotating, so because of this rotation, there will be change in magnetic flux for the armature coil, whatever armature coil is there. So remember, this is a 3-phase, small 3-phase machine. Okay, AC generator, 3-phase AC generator. So this is the permanent magnet that is providing you the field excitation for the pilot exciter. So you are getting some output voltage, which is 3-phase AC over here. So this 3-phase AC is the output of the armature from the pilot exciter. That could be controlled. So this is your 3-phase AC, actual voltage of the pilot exciter output. This provides you the firing angle control for controlling the field of the AC exciter. Okay. So basically what you are doing, you are actually controlling the excitation of the AC exciter with the help of this controller. And this is the firing angle, whereas this is the actual voltage fed to the controller. And again, remember, this should be DC. So because the output of the pilot exciter is AC, this is three-phase AC, you need some sort of rectification so that you get some DC output from here. And the control of this is provided from the voltage regulator. So this is a controlling effect. You have some controlled IF field current for the AC exciter here. So this is how it is being controlled. And here there is no control. It is simply a rotating uncontrolled rectification because you are already having some control here. So
sir, here AC exciter is the prime mover of both generator and pilot exciter. When AC exciter is acting as the prime mover.
AC exciter actually cannot work as the prime mover. There should be some, rotating mechanism.
Yes, sir. I mean, sir.
Yeah, they are on the same shaft. These four, these, and these all are on the same shaft, the shaft of the main machine. Okay. And you can use any prime mover for rotating them. Okay. But on their own, actually, they cannot rotate. You have to have some mechanism to rotate them. But they are on the same shaft. That is true. That's why they are put in the same block. But as I mentioned, you have to be careful in choosing that this field is not the field of the AC exciter. This is the field for the pilot exciter. The field for AC exciter is the lower one, this one. Okay, and again, you have some manual control mechanism also possible. If the automatic control mechanism doesn't work, then the manual control will be activated. The last one of this excitation system is the static exciter. Here, all components means the components associated with the excitation system. Okay, of course, the main generator must have some components which is rotating, either field or armature. By static excitation, it means simply we are referring to the excitation system blocks, not the main generator blocks. So all components in the excitation system itself are stationary. Again, this could be controlled and uncontrolled. And the next parts, actually, we will see in the diagram, the next 2 points. So this is the configuration, actually only one of those. There are few examples or few types provided in the book, in the textbook of Prabha Kundur. So probably you will get idea about the remaining types, but I think only one is sufficient for getting the idea how is it working. So this is static, means you have the excitation transformer. Of course, you are not going to rotate a big transformer. So this is a transformer which is stationary and which is one part of your excitation block. You have the stationary controlled rectifier, and that is also part of your excitation system. So this is also stationary. And ultimately, probably the field will be actually being rotated with the help of some prime mover. And again, you have some DC output here. So, and you have the slip ring available. So from here, you can extract the information of the DC voltage. And again, you have the magnetic contactor mutual exclusive condition, normally open and normally close, where AC voltage regulator gets the first priority. If it fails due to some reason, then DC voltage regulator will take care of the operation, but of course in a manual manner. And then you have the auxiliary inputs, again, due to the information about the limit values, okay, for protection purpose. So the excitation transformer, what it does, it basically takes the information of the terminal voltage, feeds it back, takes input. So VT is actually taken as the input side of the excitation transformer. Then you have some stepping down type of operation, because these are power electronic devices. So you must step it down to some low value so that you can operate these rectifier blocks easily. the power rating of these rectifier blocks are not violated. You have to make sure with the help of this excitation transformer. So because of this presence of excitation transformer, you see we are not using any rotating exciter, we are not using any pilot exciter, we are not using any AC generator or DC generator, no rotational device. So that's why it is known as static excitation. Okay, simply a transformer is enough. So the transformer is there. Then the output of the transformer is actually controlled and rectified. So this is the input. This is the rectification and controlling. The controlling will come, of course, either from the DC voltage regulator or AC voltage regulator. This is the power input to this DC voltage regulator. And then you have the slip ring, which gets the DC voltage to the field circuit. And that is the control. And I think the remaining few slides I have already mentioned. What is the job of terminal voltage transducer? What is the job of the voltage regulator? And the other elements like load compensator, power system stabilizer, limiter. So all are actually discussed at the beginning of today's lecture. So now, do you have any question associated with this? Or any previous blocks that I showed? Nothing. Okay, so if you don't have any question, then we stop our lecture for today. And inshallah, we meet on next Friday. Okay, so see you then. Assalamu alaikum.
Assalamu alaikum.
Wa alaikum assalam.